In this video, we're going to walk through the process from start to finish of graphing a sine or cosine curve with, all the transformations. It's going to look a lot like what we did last lesson. We're just adding this new bit, the phase shift, in at the end. So to start with, the first 3 steps on my list, I call this a 7-step process, but it's really only like 3 groups of steps. The first thing we're going to talk about is everything that goes on the y-axis. So that is the midline, the amplitude, and the range. Those 3 things go together, and we use them to make our y-axis. So for this graph, the midline, because our k is -2, the midline is just y equals -2. The amplitude is 2 because of our a. And the range, therefore, would be, if we're centered at y equals -2 and our amplitude is 2, we go as low as -4, as high as 0. So those 3 things go together, and immediately I'm going to use that to build my y-axis. Notice how all of those values are negative. This graph never gets into positive territory. So when I graph my x-axis, I'm going to put the x-axis near the top because I only really need space below the x-axis, not above it. And I will scale this. I'll have each one of these boxes be 1. I could fit more, but... And so our range is going from -4 to 4. And so I will go back to this and make my nice dotted line at -4 and 0. Sorry, my range is from -4 to 0. With the midline at -2. And yeah, you can't really see that top line, but it's there. Okay, that's steps 1, 2, and 3, which is really all one big step. Okay, our next piece, the next thing we're going to talk about, go together again in pair. It's the period. And we're going to use the period to label the x-axis. I consider that its own step. And we know the formula for finding the period is 2 pi over b, but hey, look here, that b is 1. So we don't have to worry so much about the period. This one turned out to be easy. It's just 2 pi. Notice how there was no information about degrees here, so I'm going to stick to radians. And then labeling the x-axis, I am going to use 3 marks for every section here, because I've got lots of space. And so this is 2 pi. Halfway point is pi, and half of that is pi over 2. Notice how I put my labels above the x-axis, which isn't really normal, but because my graph is going to be below the x-axis, I figured might as well make it as readable as possible. Okay, the next piece is a 2-step process. We did step 6 last class also, where we plot the 5 points. And when I say the 5 points, I mean from the parent function. And because this is a sine curve, when x is 0, it would start at the midline and go up to the max, and down to the midline, and down to the min, and back to the midline. So those are the 5 points of the parent function. But like we saw in the last example, we're not ready to connect the dots yet because there is a phase shift. And so what we're going to do is literally move those points over. If it's getting too cluttered on your screen, on your page, and you don't want to draw these original points and draw the little markings moving them over, that's fine as long as you're putting the final points in the correct spot. I think it is incredibly helpful to see this phase shift. So our phase shift, based on our h, x minus pi over 3, means that we are going to be moving forward pi over 3. In order to do that, I need to figure out what pi over 3 is. If it helps you to think in degrees, it's not the end of the world here. Pi over 3 is 60 degrees, and each quadrant, each pi over 2, is 90 degrees in this example. So pi over 3 is exactly 2/3 of a quadrant. This is why I decided to make my quadrants be 3 boxes wide. I looked ahead, I saw the phase shift, I knew that how pi over 3 compared to pi over 2, so I thought, all right, well, if I do it this way, I can make each phase shift be exactly 2 boxes, because each quadrant is a total of 3 boxes. If you don't think ahead and you don't plan like that, it's not the end of the world. It just means that you're going to have to estimate a little bit when you do your phase shift. Like had I done 2 boxes for every quadrant instead of 3, I simply would have had to think, okay, well, pi over 2 or pi over 3 is 2/3 of the way to pi over 6. Sorry, 2/3 of the way to pi over 2. And so I would have to figure out, well, 2/3 of 2 boxes is like 1 and a little bit boxes. So it's not the end of the world if you have to do that. But if you can think ahead and recognize what your phase shift is going to be and plan your x-axis accordingly, it makes your life a lot easier in the end. One very important detail. As long as you are within range of your x-axis, which you're almost always going to be, your job is to include, I'm sorry, I said x-axis, I meant y-axis. Your job is to include the y-intercept. If I were to just connect these 5 points here, I wouldn't get all the way back to the x-axis, to the y-axis, and see my y-intercept. So what I want you to do is, when this happens, you are going to need to add another point to your parent function. It would have been the point before the first one that we did. So one more quadrant over is another 3 boxes. The parent function would have been down at the midline, the minimum. And so the phase shift from there is 2 boxes there. So now I see where I'm headed to here. And now you can see that approximately where that y-intercept happens. That is the last little bit I want to make sure you're doing. So sometimes when we say 5 points, it actually ends up being a little bit extra. We're going to do the next example also. It's the same process, the same steps, so we'll do it right here on the same page. But there's one important thing I want you to notice about this one. When we write the sine or cosine curve, we should see it as y equals a times the sine of b times x minus h. Of course, that x could be a theta also, plus k. What's important here is that inside the argument of that sine, and it works for cosine also, b times x minus h, the b is separated, pulled out from the x minus h. So if there is a phase shift and a period change, the b that tells us how to figure out the period has to be separate, factored out from the x minus h. We saw this before with radicals, we saw it with logs, it's the same thing here. Had I written this without those extra parentheses, had it been cosine of 3/2 theta minus 90 degrees, minus 5, it would be your job to recognize, oh wait, this inside argument right here has not been factored out. The b has not been separated from the x minus h. So before you identify the h, you would have to factor it out. Factor out the 3/2, which means dividing 90 by 3/2, which would be 60 degrees. And so notice how this equation and this equation are not the same thing. That presence of the parentheses really does matter. So if it's not there, it is your job to put it there. In the example we're graphing right now, it's already there. So we don't have to worry about that. I'll use the same color coding for all of my steps. We'll start with the midline, the amplitude, and the range. The midline is that y equals -5. The amplitude is 1. And so the range is from, again, we're only negative here, -6 to -4. So again, when I make my x-axis, I'm going to think about that and plan ahead and draw my x-axis all the way at the top here. So that I have plenty of space for my -4 to -6. I don't have quite enough room to count by 2's here, so I'll count by 1's. -1, -4, -5, -6. You certainly can label all of the points in between if you want. But as long as my scale is even, and I show my maximum, my midline, and my minimum, we're in good shape. Okay, y-axis, done. Think of those as one step. Move on to the x-axis, which means we think about the period. We identify that b is 3/2, and so our period is 360 degrees. Notice how I'm working in degrees because that's what the problem indicated. Otherwise, I wouldn't. Divided by 3/2, and that is 240 degrees. Which means that each one of my steps here is 200, if I count 4 steps, that is where I hit 240 degrees, 120 degrees here. And you know what I'm noticing? Look, as you're doing this, I'm looking ahead. My phase shift is going to be 90 degrees. And if I think about 120 degrees, like comparing 90 degrees to 120 degrees, or comparing 90 degrees to 60 degrees, if I were to keep going there, 90 degrees is 1.5 quadrants here. So it's a little bit inconvenient that I've divided my quadrants up into boxes, into 3 boxes. So I haven't gone too far. I'm just going to erase that and say, you know what, in this case, it'll be easier for me if each quadrant is only 2 boxes. Because then my 90 degrees will be a nice even 1.5, or 3 total of 3 boxes, or 1.5 quadrants. So that sort of planning and adjusting on the fly, definitely, 60 degrees, definitely helps make your graph easier to finish at the end. Okay, so we've got our quadrants, we've got our y-axis. That means we can plot our parent function, the 5 points from the parent function. Notice that this one's a cosine, so we would start at the maximum. Be on the lookout for when there's a negative in front of that, which would mean we would have to draw this upside down. And in this case, my phase shift is actually pretty big for this graph. The phase shift is backwards. No, it's not. It's forwards 90 degrees. One slight problem with that, if I plan ahead, if I'm moving forwards 90 degrees, that means I'm going to need some points back here. So what I'm going to do is keep going back here and graph the 2 points before that. So that way I can take all of my points, move them forwards 90 degrees. And again, 90 degrees is a total of 3 boxes, right? That's 30, 60, 90 degrees. So every one of these points is going to be moved forward 3 boxes. You don't want to be too heavy with those curved lines, those dotted lines there. Because the point, what we're trying to graph, is that the dot. And because I told you before I like to see the y-intercept, I needed to move, this is why I needed to add those extra purple dots to begin with, because I didn't go far back enough to cross the y-axis. But now I do, and so now I can just draw the curve the way we know it looks. through all of those points. Make sure that before you put your arrow at the end, you turn so the arrow doesn't go outside of our range.